This is part 2 of section 5.7 dealing with trig inverse integrals. This video is more of an overview of maybe some strategies as to how to approach certain integration problems, because at this point we've learned all the integration rules, we've learned all the definitions. Now it's just a matter of figuring out when to apply them and under what conditions you apply which rules. So I made a list of the integration techniques that we've learned so far. These aren't the rules, these are just techniques. We've done the U sub, U manipulation, we've done one section that had long division. An integration technique that comes up a lot is to simplify the integral by either factoring out constants or splitting them up. And then as far as trig inverse ones, to me it's just a matter of matching the pattern. So these are the two trig inverse, just a matter of matching the patterns for finding trig inverse integrals. So I'm going to go over 3 problems and then give you guys one U-try problem at the very end. So the first one's going to be find this integral. The first thing I notice is that I have a trig inverse function and the derivative of it is also in the problem. Because if you recall from the previous section, if you have arcsine, the derivative is the square root of 1 minus the variable squared. So if I have a function with its derivative as the other part of the problem, first thing that comes to mind is to do a U sub. So for this one I'm going to do a U sub. I'm going to let U equal the sine inverse of x, because the derivative of sine inverse, or the derivative of arcsine is, well, basically the U prime is just going to be the derivative of x, which is 1, so it's going to be 1 over square root of 1 minus x squared dx. So this aspect of it takes care of the du, and then u is going to be the numerator. So the rewrite portion of it is going to be a u and then du. And then you can think of this as u to the first power, so the antiderivative of u to the first power. I can do the power rule, which is u squared over 2 plus c. I don't have any limits, so I go back to what my initial u was, so it's going to be sine inverse squared of x. I'm going to write all of that squared all over 2 plus c. And that's my answer for number 1. Right, number 2, I have integral of x to the third over x squared plus 1. First thing I notice is that I have a bigger term in the numerator, a bigger power in the numerator. So that means I can do a long division, because I can divide a bigger number, a bigger term, by a smaller one. So long division is what I'm going to do. Alright, so long division, I'm going to go x to the second plus 1, x to the third. This just multiplies it by x, so it's going to be x to the third plus x, switching the signs. So I ran out of whiteout, so I'm going to have to just put this as negative and then bold that as negative, so this reduces out. And so this drops, my remainder is just going to be a negative x, so it's going to be minus my remainder over what I divided by, so x squared plus 1. So the way this expression divides, this is the same as saying the integral of x minus x over x squared plus 1 dx. And so even though we did long division, now I have to go to another technique, and that's just going to be simplify the integral. What that means is I'm going to go ahead and split this up. So I'm going to integrate this piece by piece. So the integral of x dx minus the integral of x squared plus 1 dx. Now this over here on the left is just a straight power rule. This is just going to be x squared over 2 minus. However, this one over here requires a u sub. So within these techniques, it could be that you use them multiple times, or you use multiple techniques. So we first did long division, Then we split up the integral. Now for this specific integral, I have to do a u sub. So hopefully you've gotten really quick at these. U is equal to the denominator x squared plus 1. The derivative of that's going to be 2x dx. I don't have this constant divided over. So this becomes the integral of, I let u be what's in the denominator. I'm going to replace x and dx with a 1/2 du, so it's going to be 1/2 du. So continuing, this integral is going to, this answer is going to stay x squared over 2. This 1/2 is a constant. I'm going to factor it out, so it's going to be 1/2. This is the integral now of u to the -1 power. The integral of u to the -1. I can't use the power rule because it's a -1 exponent, so it's going to be a natural logarithm. So this turns into x squared over 2 minus 1/2 ln absolute value of u plus c. And last thing is plug back what I selected for u on this one. So my answer is x squared over 2 minus 1/2 ln absolute value of x squared plus 1 plus c. Okay, so if you have any questions, I can go over this tomorrow with you in class. And the last one that I'm going to go over, and then a U-try problem for you guys, is this one. It's finding the integral of dx over square root of x 1 plus x. Now I'm just going to go ahead and try something and see where it takes me. The first thing that maybe comes to mind is to do a u sub, but just by kind of starting a u sub, if I let u equal 1 plus x, the derivative of that du is just going to be dx. I don't have the square root of x accounted for, so I'm leaning that I'm probably going to have to do some sort of u manipulation. Okay. So maybe not letting u equal that. Maybe what if I just let u equal the square root of x? And you can think of this as x to the 1/2. Well, if I do a derivative at this point, the power rule says 1/2 x to the -1/2, which would be 1 over 2 square root of x dx. I don't have an additional square root of x in here because I've already used this as my square root of x, and I don't have this 1 plus x accounted for. So maybe I shouldn't take a derivative at this point. So kind of finishing this up, maybe I'm going to let u equal square root of x, but before I take a derivative, I'm going to square both sides. So this is a u manipulation aspect of it. So the u manipulation is going to be squaring both sides, so I have u squared equal to x. Now I can take a derivative, so now this is going to be 2u du is equal to dx. Because now when I rewrite my integral, x is going to get replaced with 2u du. I'm going to replace square root of x with u. And since I have 1 plus x, I'm going to replace it with 1 plus, well, x is the same thing as u squared. Right? So, notice I have a u and a u in the numerator and the denominator, so that reduces out. This 2 is just a constant, so I can factor that out. So it's going to be a 2 factored out with du, and it's 1 plus u squared. And notice I have a constant plus a variable squared. And not only that, I have a constant squared plus a variable squared. And that matches the arctangent pattern. In this case, the constant squared is 1, which is going to be rather easy, so 1 over 1. So this now matches the arctangent pattern. I'm just going to put tan inverse pattern. So this started off as a U manipulation and turned into matching one of the arctangent patterns. So it's going to be a 2, and again A is the constant, so A is going to just be 1, so it's going to be 2 arctangent of x plus c, and that's the answer. So kind of, I guess, talking my way through this is, I started off with the u sub, but I didn't have the correct du, so I crossed that off. So then I let u equal the other part of the problem, being the square root of x. But because if I take a derivative here, I didn't have this extra square root of x, I went ahead and did a u manipulation to get everything from x's and dx's over to u's and du's. So it's kind of like a way you can problem solve your way through a problem. Alright, the last one is a u-try problem. So I'll go ahead and I'll give you time to pause it, try it, try the technique, any technique you can think of, and we'll go over the answer tomorrow in class when I walk around and check your notes. I'll check that you've attempted this problem and that you have it right. And that's it.